Forget the sci-fi movie tropes and the Matrix glitches. Peer-reviewed research into the simulation hypothesis now relies on the same formal tools used to study the early universe and quantum computing. Identifying the nature of our reality is a technical challenge. It requires reconciling evidence from across formal logic, quantum physics, and pure mathematics. The central question scientists are trying to resolve is whether the universe is composed of continuous physical matter or if it functions as a discrete, optimized data system. Traditionally, we assume space and time are continuous. In this framework, the universe is an unbroken grid where matter exists independently of whether it is being measured. This diagram shows the contrast. On the left is the traditional grid of continuous physical space. On the right is the alternative, a node-based network where reality operates through algorithmic information processing. Solving this debate requires an evaluation of three specific pillars: statistical probability, physical quantum limits, and mathematical unfalsifiability. The first pillar investigates the statistical axioms. This evaluates the mathematical probability that a civilization like ours exists at the base level of reality. The second pillar looks at the physics of information systems. We will analyze quantum mechanics to see if physical matter exhibits the resource-saving behaviors found in computer rendering. The third pillar focuses on algorithmic bounds. This tests the limits of mathematics, asking if it is possible to prove the simulation hypothesis from inside the system. We will follow the historical timeline of this debate, beginning with pure logic and moving down into foundational physics. Before we can examine the physical universe, we must accept the baseline math. Statistically, human existence is a mathematical outlier. The academic debate began in 2003 when Oxford philosopher Nick Bostrom published a paper detailing what is now known as the simulation trilemma. Bostrom's logic proposes three possibilities. Option 1, civilizations go extinct before developing simulation technology. Option 2, they develop it but choose not to simulate ancestors. Option 3, simulations are ubiquitous. These nested realities multiply exponentially, so simulated entities would vastly outnumber real ones. In 2020, Columbia University astronomer David Kipping applied Bayesian probability to this trilemma to see how the numbers actually distribute. This distribution curve maps Kipping's analysis. By grouping the two physical baseline options, extinction and abstinence, against the growth of ubiquity, the probability that we are currently in a simulation lands at just under 50%. Pure statistics cannot confirm the simulation. But mathematically, these figures shift the burden of proof onto anyone claiming we exist in base reality. Physicists are now testing whether the physical universe behaves with the resource-saving efficiency of a computer. In quantum mechanics, a particle exists as a probability wave. It collapses into a definite state only when measured. Observation creates its location. This mirrors video games. To conserve power, a rendering engine only draws the environment when a player looks. If the universe processes information, physical space must have a minimum resolution, like a digital screen. Space cannot be divided infinitely. At exactly 1.616 times 10 to the negative 35th meters, the Planck length, our laws of physics break down. It acts as the indivisible pixel of the universe. In 2026, physicist Dr. Melvin Vopson published an analysis on the second law of infodynamics. This chart tracks his findings. While physical entropy increases, information entropy in natural systems optimizes. It behaves like a digital system organizing data to save space. Based on this compression behavior, Vopson argues that information is the fundamental substance of reality rather than matter. In October 2025, UBC Okanagan researchers published a paper claiming to have mathematically disproven the simulation hypothesis. Dr. Mir Faisal's claim rests on the idea that the foundational level of reality relies on non-algorithmic physics, processes that do not follow programmed rules. Because algorithmic code cannot generate non-algorithmic phenomena, his team concluded that a computer program could not produce our universe. However, the work of mathematician Kurt Gödel exposes a logical paradox in the UBC paper's conclusion. Gödel's first incompleteness theorem states any formal system contains true statements unprovable from within. For simulated beings, it's mathematically impossible to map the base reality running outside. If a simulation hides its parent code, boundaries naturally appear non-algorithmic. The attempt to disprove the simulation actually showed the hypothesis is strictly unfalsifiable from the inside. When statistical probability, quantum resource management, and mathematical incompleteness are viewed together, they suggest a reality that operates with the efficiency of a computed system. Statistics indicate that existence in base reality is a minority position. Quantum mechanics and information physics mimic the behavior of an optimized rendering engine, and Gödel's incompleteness theorem explains why we cannot observe the system's code from within. While these pillars do not provide absolute proof, they provide a consistent framework for the simulation hypothesis that cannot be dismissed by current physical observations. Accepting that reality might be algorithmic often creates a sense of existential dread. But philosopher David Chalmers argues that our definition of real needs to be more precise. Information is reality. Even if the underlying substrate of our universe is digital, a simulated thought and a simulated consciousness are both functionally and mathematically real. If you were removed from this system, the version of you defined by this universe's laws would cease to exist. We do not need to exit the system to validate our existence. If the universe computes consciousness, then you are a genuine mathematical output.